Hello and welcome. Today we're going to talk about the exponential and logarithm functions. These functions are, we've already studied a bit of the exponential function, but let's just write that down. So we have e to the z. We're going to call that f of z for now. E to the z, of course, has some really nice properties. One of them is that we can rewrite this as e to the x plus e to the I y, because that is e to the x plus I y. And that's because exponents sum. The product of two exponentials can be written as the sum of the exponents. All right, so we also know some other properties about this. We can rewrite this as e to the x plus cosine y plus I sine y. And from the Cauchy-Riemann equations, we know that ux is going to be equal to e to the x cosine y, and and vy is going to be equal to e to the x times cosine y. All right, so those two check out to be equal to each other. And then also we have uy is equal to negative sine y e to the x, and vx is just going to be equal to e to the x sine y. But if we take a negative of that, of course, these two then check out as well. So, and this is true for any value of x or y, and these are smooth, continuous functions. Therefore, f of x e to the z, f of z e to the z is analytic entire. Okay, and entire just means that it's analytic on the entire complex plane. It also has, so for instance, we can solve equations like this now. E to the z is equal to 1 plus I. All right, we might want to write this now in a different format. This, the value 1 plus I is just the point 1, 1 in terms of a vector, if we want to put in vector notation. And of course, that has a magnitude of square root of 2, a modulus of square root of 2, and e to the I pi over 4. But we got to do one thing. We always have to do this. There's this multi-valued nature of when we write in polar form, so we can write that like that. So where k is equal to 0, plus or minus 1, plus or minus 2, and so on and so forth. Forever? All right, so clearly we can see that if we equate this to e to the x, e to the I y, we find that, so we want to find and solve for our z, find out what the z values will generate this, and so we clearly see that e to the x has to be equal to root 2. Therefore, we can write this as x is equal to natural log of root 2, because this is a real valued equation that we're solving here. Likewise, we see clearly that y then has to be equal to pi over 4 plus 2 pi k. Okay, so there's lots of values. We can say that this is maybe the principal value. And then there's all these additional ones for when k is not 0. Okay, so we see that there's a multi-valued nature to this. And so we always have to watch out for that whenever we're dealing with exponents and such. There are many values, many z values, so we could write that like this, right? So we know now that right somewhere around there is natural log of root 2, but then we find out there is a value at pi over 4 on the y-axis, but then there's a bunch of them that go up. So there's one up here every 2 pi intervals, and so on and so forth. There's another one, and another one, and so on and so forth. And there's also the ones below. So every 2 pi interval. So there's lots of values of z that generate the given function. And that's this the notion that e to the x is a periodicity. Okay. All right, so we've studied the mapping of e to the z before, and we'll, if you need to refresh your memory, you can go back and watch that video. But now we want to talk about how to take an inverse. We want to find a better way to solve this equation. Given that there's this multi-valued nature, of course, there's not just one value of z that solves this equation. So in general, we want to be able to solve this equation, at least find one value, given w is some sort of fixed value in the complex plane. We want to find if what z's generate that w. So what we need to find a way is inverting this equation. Okay, so of course, if we have this equation, e to the z is equal to w, and I want to solve for z, if you will. Of course, if we had e to the x is equal to y, we would take the natural log of this thing like that, and you'd get x is equal to the natural log of y. All right. But now we need to see, is there a way to invert this equation when we have it like this? So of course we can do something similar. E to the z is actually e to the x, e to the I, y, right? And that's equal to w, and w is actually equal to, we can write it in this form, r e to the I, and then we're going to have a, what I'm going to call capital theta plus 2 pi k, right? Where k now, of course, as always, 0, plus or minus 1, plus or minus 2, and so on. Okay, so how do we solve this equation? Well, we just have to equate things. E to the x is equal to r. Therefore, x has to be equal to a natural log of r. All right. But now, and then y then has to be equal to this value here. And so this value here, I'm going to call that the principal argument. Of w. So what I mean that is arg of w is equal to capital theta. Okay. And of course this is in between pi and negative pi. Okay. And that's going to be plus 2 pi k. All right, so again, there's multiple values. Multiple values that can generate this particular w. Okay, so in generally we can formalize this process now, and I want to do that. So the idea here is I want to define a function, call it complex log, and we're not going to use the natural log ln notation. We're going to say log, log, of e to the z has to be equal to z. Okay. And the idea here is I want to define this function here that is the inverse to e to the z. Now clearly we have a problem. How can we invert a function that has multiple values equal the same? So there's not a straightforward way to do it, but we can find a way to restrict our domain so that this is a meaningful statement. So let's get another sheet of paper out here. So what I want to do then is I want to define log of z. All right. So just from before and we want to find out that's equal to w. So okay, so now I'm going to flip things on their head a bit. I'm going to call z is equal to hold on. So I'm going to say that. And so that's equivalent to saying that e to the w is equal to z. Okay, so so I've just reversed the roles that z and w played on the previous page. So that's going to be called r e to the I, and again I'm going to write that as the principal argument plus 2 pi k. All right, and that means w is equal to natural log of r e to the I capital theta plus 2 pi k, all in parentheses there. And of course, the natural log, this is a log like that. The natural log should have a nice property that it turns into natural log of r plus I capital theta plus 2 pi k. All right, so we see here that this is multiple valued. So it's not a true function. The logarithm function of z equal to w is not a true function because it's multiple valued. It's generating all these different imaginary values. So what we have to do is restrict the domain. So we're going to restrict our domain. We're going to say z now is part of this domain is going to equal say z, and it's going to be r is greater than 0. Okay, we can't have r being 0 because natural log is not defined there, right? And also we need to define an alpha less than. We need to restrict the domain so that we have a log of z is equal to some value of theta. So we have natural log r plus I theta, right? So with this definition, we need to define a theta then that's that's going to be between alpha and alpha plus 2 pi. Okay, in this case then, so if we have z is equal to r e to the I theta, right? So if we restrict it within this domain, then this function will always be unique. It'll have a single value. And so we call alpha is called a branch cut. And we get to choose. The branch cut. We can choose it to be anywhere we like. Standard is to pick alpha is equal to negative pi, in which case, of course, we're only going to consider a domain z of the form negative pi to theta all the way to pi. And of course, this is an open set. We can see because it has strictly less than signs there. All right, and this set looks like so. So this set, then you can write it like this. It's just sort of there's the 0 point. Sometimes you just sort of like put a little like that around it. People kind of cross it out like. That's the branch cut. That's why we call it a branch cut. We're cutting that line out. So that line right there is now no longer in our set. And then z can then be anywhere in here. And our theta value is restricted to this strip. Okay. All right. So with that, then we have a unique valued log function. Okay. So of course, the log function then, it makes the mapping then to a real value or an x value that's natural log of r, and then the theta value is going to be between alpha and alpha. So our imaginary part of w, this represents w right there. Imaginary part of w is then going to be between alpha and alpha plus 2 pi. So the range or the image of this branch cut is going to be all this strip in the w plane. Okay, so that's a good example of what we're doing here. So again, standard is to choose the branch cut to be right there. So so I'll just state without any kind of proof, but we're going to state that the derivative of z, and you can check this out pretty straightforwardly. That's going to be 1 over z, just like we've normally seen before. So that's a nice result. And this comes from just checking the Cauchy-Riemann equations in polar coordinates, which is the easiest way to do this one. So maybe we will actually go over that. So in polar coordinates, we can write the Cauchy-Riemann equations become r u_r has to be equal to v theta. And also, u theta is equal to negative r v r. Okay, so remember that log of z is equal to natural log of r plus I theta. Okay. So again, this is u, and that's v. Okay. So ur is equal to 1 over r. If I multiply that by r, I get 1. V theta is equal to 1. That checks out because these had to be equal. Likewise, if we have, if I write, if I go u theta, that's equal to 0 because u is not a function of theta. Likewise, Vr v is not a function of r, so it's also 0, and that also checks out. So the other Cauchy-Riemann equation checks out. Okay, so then the next question is, how do we find it? And so you'll have to go back in the book in the polar coordinates section. For the Cauchy-Riemann equations in polar coordinates, if you actually want to find the derivative, what the derivative is, it's always df dz is equal to e to the I theta, e to the negative I theta times ur plus I vr. All right, so we can write that out. Ur, of course, is equal to 1 over r, and that's equal to e to the I theta, negative. And then vr is I times 0, so this becomes 1 over r e to the negative I theta, which is precisely 1 over z. Okay, because we're taking z to be r e to the I theta. Okay, and of course you can look up this version of the Cauchy-Riemann equation in the textbook. It's fairly straightforward to derive that. Okay, it involves a change of coordinates from Cartesian to polar coordinates, so it's fairly straightforward. Okay, so the next question then is, what about logarithm rules? Okay, so a standard logarithm rule is if I have some function, some value. So this is for a real valued. So for a real valued log function, we're going to take, if I have some value x and I take, to the nth power, we know that the power comes down, like so. Okay, we need. The question is, does such a thing happen in the complex plane with the complex log function? And the answer is no. So we got to figure out why. So let's just do one example, a counterexample of why this doesn't work. Let's talk about log of I to the third power. Okay, so let's write this now. That's log of, that becomes negative I if you multiply I 3 times over, okay, which is log of e to the 3 pi, we need the principal value here. So we're going to take alpha equal to negative pi. So anytime we write this function, we always have to, in a parenthetical somewhere, say where our branch cut is. And I'm going to say it's at alpha equals negative pi. Okay, so I'm taking the negative real axis to be the branch cut. All right, we always have to do this. There's an asterisk. Every time you use a complex logs function, you have to choose which branch cut you're using. And depending on the problem, you might choose a different one. It really depends. You usually want to keep it somehow far away from wherever you're doing your calculations. So we'll try to we'll be using that idea more and more in the future. So in this case, we're going to have to go e to the I, and I'm going to say now that's going to be negative pi over 2, okay, because negative pi is down there, or negative I is down there, and that's going to be negative pi over 2 to get there. Okay, of course that's part, remember I've taken, this is where my branch cut is, so I can go that way all the way to pi, and I can go this way all the way to negative pi, up to negative pi, right? Those are the angles that I have available to use, so I have to use that principal value inside there. And of course we know that that's going to be natural log of r, which is 1, plus I to the negative pi over 2. Okay, so there's a good example calculation of how to use the complex logarithm. So now let's try doing the other thing. Let's check if we can bring power down. Okay, so that is, I want to check if log I to the third power is 3 log of I. Okay, and I'm going to Again, I'm going to put a question mark on this, whether these are equal. All right, so we're going to, we don't know if this is equal yet, and it turns out it won't be. But let's verify that. 3 log of I, and that's going to be e to the I pi over 2 positive now. Okay, and so that again is also, that's right here, so that's within our domain. And so we can now go 3 times I times pi over 2. So remember, this is 0 here, and that's plus, and that becomes negative I pi over 2. And this is 3 pi over 2I. And it's clear that these two are not equal. So no, not equal. And so it turns out this property does not work in the complex plane. So we're going to have to be careful on how we use this stuff. So I want to go over a few more examples of calculations of the complex log. And again, I'm always going to take my branch cut to be on the negative real axis. So let's try a log of 1. All right, it should match up that that is somehow continuous with this to be 0, right? So this is the real valued natural log. And that is going to be log of e to the I of 0, okay? And that will be 0. Now if I take a multiple valued log, so I don't take a branch cut, then that becomes log of 1 is actually e to the I, and then I put in parentheses k to pi, right? And then the answer then is I, k to pi. So there's all the possible values for k is equal to 0, the principal value that we're interested in, and plus or minus 1, plus or minus 2, and so on and so forth. But now let's try another one. Let's try log of negative 1. All right, so this is an example now that our branch cut alpha equals negative pi can't work, because by definition theta for this one is equal to pi. And we said that we were restricting our domain, that this couldn't exist. So we're going to have to take a different branch cut. So we can choose any branch cut we like. Let's try going to negative pi over 2. Okay? So in which case, then we can now use our, actually calculate this. So this becomes logarithm. This becomes logarithm of e to the I pi. And of course we can write that as equal to I pi. Okay, so there you go. That's how you do it. And you know, you'd think that this is sort of silly. I mean, I could just write this like that all the time. But it turns out if we do other calculations, we're always going to have to choose that branch cut, because when we if something interferes with it, for instance, if I take you know, log e to the I pi here, then I multiply it by something else like e to the I you know, 24 pi, for say, maybe I want to you know, do something here, and it's going to change things depending on which branch cut I take. Anyway, those are examples that we can go and deal with later, but this is just to get you started. Hopefully this clears up a few things, or just kind of gets you used to doing computations with the complex logarithm function. So thank you very much.